Electrostatics is a little bit more involved than the gravitational fields, and it is because there is some of the stuff that you don't really see in your SAGs, but it's assumed that you know this because you've done it in previous years. So I'm going to quickly look at the stuff that you did in grade 8, 9, and 10, depending on where you are, and that is assumed that you know. Okay, the first thing, these prefixes. Please remember that in this topic they pop up, but they can come in any of the sections. You need to know pico, nano, micro, milli, centi, deci, kilo, mega, giga. Giga and tera, I can't say that they ask a lot, but please know these because just in general it's good to know. And then also know that if you see this symbol, the symbol can be replaced by times by 10 to this. So if you have 5 nano coulombs, you can say 5, and instead of nano, you're just going to write times 10 to the minus 9. So 5 times 10 to the minus 9 Coulomb. Do this conversion first because it does count mark. So any conversion that you do is worth a mark. Now, from previous grades, you needed to realize why something gets charged. So to get charged, the only particle that can leave an object, I'm hoping that you remember, is an electron. So if you look at a neutral object, you have equal amounts of protons and electrons. So this would be our neutral object. Now, if you look at this one, there's still 1, 2, 3, 4, 5, 6, 7, 8 protons. And if you look at the electrons now, there's 1, 2, 3, 4, 5, 6. So there's not, in this one, there's not the same amount of protons than there are electrons. So this would be a neutral object. So the charge would be 0. So this one would be, then they are more positive, so the charge would be positive. There are more negatives here if you count them, so the charge would be negative. So to get charged, an object must either gain electrons or lose electrons. So the one that's positive lost electrons. So electrons left that object, and the one that's negative gained electrons. Now, often they ask you how many electrons something has in excess or how many electrons has something lost, but it's more often done when you have to share the charges. Just remember that electrons are measured in coulombs. And these equations are not on your information sheet. I don't really want you to go and rote learn these equations. Make sense of it. Because if you charge is measured in coulombs. Now remember, an electron has a specific charge. So if I have 2 coulombs of charge, that actually means I have a whole bundle of electrons. So if you look at the charge of, so this is my total charge. So we can actually say that that is Q total. And it has, let's say it has a negative charge. So if it has a negative 2 charge, it means that it is 2 coulombs of electrons extra. Now, if you look on your information sheet, and this is why I don't want you to go and rote learn because people get it wrong, on your information sheet, there is the charge of 1 electron. You can see magnitude of the charge of 1 electron. And it's magnitude. It's only size that's really important here because we're working with number of electrons. So you just have to know, is there extra electrons or is there a lack of electrons? And we've said that now already. So this is the charge on 1 electron. Now, if you want to go and get the total charge of the number of electrons, you have to say, right, this is my total charge. I want to work out what is the number. I always use a hashtag for number of electrons. So the number of electrons, this is my total charge. So it's going to be my Q total. Again, there's no equation like this. You make logic sense of it. This is my total charge. And you want to know and you know the charge of 1 electron. So the charge of 1 electron is 1. What did we just say? 1.6 times 10 to the minus 19. And that will give you your number of electrons. Now remember, electrons are tiny little things and there are millions of them. So if you here end up with a times 10 to the negative, you must know you've swapped your values around. You're going to end up with a huge amount of electrons. Your answers must make sense. Now these are still done relatively okay. Then for the sharing of charge. Now remember, charge, you did conservation of charge in lower grades. Conservation of charge means that the total charge must stay conserved. It can go from one object to another, but it can't be lost. So if you have two objects, one with a zero charge, which means it's neutral, and one with 8 extra electrons, what's going to happen when they touch is that the electrons will spread. Remember, they're negative and they will repel each other. So they will spread evenly between the two objects. So this one would then end up with 4, and this one would end up with 4. And when they split up, they will each have 4 electrons. Some people also teach an equation for this, but like I say, always make logical sense out of it. You go and look at what is your charge, your total charge of the two together. So let's say this was 8, had a charge of minus 5 coulombs, and this one has a charge of plus 8 coulombs. Normally the charges would be given to you in coulombs. Remember, it's number of electrons that we're looking at here. Now, if we touch these two, so we need to look at how are they going to spread out the charge if we take this object and we almost make them one because they're touching. So if you look at the total charge, now here I'm going to end up with a total positive 3 charge because the electrons are going to cancel out until they have the same charge. So we're going to end up with plus 3. But now when they split up, they're going to share that charge. So the one will end up with 1.5 positive coulombs, and the other one will end up with 1.5 positive coulombs. Now in this, when you get a question like this, they're not going to ask you how many electrons were there extra. They're going to say to you how many electrons were transferred. So the first thing you need to realize is that the negative one is going to lose electrons and the positive one is going to gain electrons. So you need to figure out how many electrons moved from here to here. Now let's see. This was, so I had a plus 8 here. I have a plus 1.5 now. I had a minus 5 here. I have a plus 1.5 here. So it's basically the difference between where you started and where you are now. So how many electrons went over? So we're going to measure it in coulombs again. So it's going to be 6.5. I hope my math is right. So 6.5 coulombs of electrons went from here to here. And now if they're asking you how many electrons that is, you have to say, fine, I have my total charge, so the coulombs of electrons that went over is 6.5, divided by the charge of one electron, and that will give me again my number of electrons. Please remember this. Very general, you need to remember, and we're going to look at that now again when we look at forces. Positive charges will repel each other, negative charges will repel each other, opposite charges will attract. You've done this since grade 8 or 9, so that you should be happy with. And that's basically the revision of what we have done already. Just also remember, if I have a neutral object, so if I have a plus minus here, and I bring something close that is negatively charged, and you actually do this in chemistry as well. So what happens is it will induce a charge on this one. So the negatives here will repel the electrons there, which leaves an excess of positives here. And that is why a neutral object will also be attracted to either positive or negative, because the positive or negative will induce a charge on that neutral object. Just remember that as well from grade 9 and 10. Don't want to go back, going forward. All right, so the first thing we're going to look at is electrostatic force. So again, please, a lot of the stuff here is exactly the same as what it was in the gravitational fields. So you already know now that like charges repel and opposite charges attract. So that's the one thing that's different. In gravitational field, it was always attraction. Now it can be repulsion or attraction. But please just keep it simple for yourself. You don't have to go and work with pluses and minuses in calculations, because you can just at the end, once you've calculated your force, you can just say it's an attraction force if it's two positives, or it's a repulsion force, or say to the left, to the right, up, down. Remember, we like English when you're answering your questions. Now, if you wanted to put it in a calculation, here you can see a positive times by a positive will give you a positive. A negative times by a negative will also give you a positive. So if your force answer ends up being positive, if you now really want to put the charges in there, you will get a repulsion force. A plus times a minus gives us a minus. So if you get a negative, then you know that they're going to attract. So positive answer will repel, negative answer will attract, if you want to put the signs in. But as I said, always just put a direction at your final answer. Now this is going to look very similar. We have an attraction force or a repulsion force, but please remember the force of charge 1 on charge 2 is the same as the force of charge 2 on charge 1. Now, I really like when you put it like this. You're going to say the force between 1 and 2, the force between 2 and 1. They are the same. You can actually use the same thing here. But when you're going to look at the vectors questions, yes, there's going to be vector questions. If you look at the vector questions, then it makes sense to put it like this, because then you can see between which two objects the attraction or the repulsion force is. Now again, for the law, it tells you 2-point charges will have a force on each other. The force is directly proportional to the product. Look, there's a multiplication there again. It's above the line. Product of the two charges, and inversely proportional underneath the line to the square of the distance between them. And that gives us the equation. Now, I'm not going to do calculations on this. Please remember that you don't have to put the charges in there. Just at the end, say whether it's an attraction force or a repulsion force. There's a lot of practice in your past paper questions for this. Also, again, remember it's a force. So the force is between two charges. So there's going to be two Q's in your equation. The same as in gravitation, if they're asking you for a field, which we're going to get to just now, you're only going to have one Q. Now, this last point here is where the vectors comes in. They say determine the resultant force on a charge if there are three charges in one dimension or two dimensions. Now, what do they mean? So we quickly have to look at vectors. Now, for vectors, what they're going to do to you, for example, is you're going to have, just move this away as well. You're going to have, for instance, a positive charge here. I'm not going to put sizes because the calculations you can practice. I am just going to show you the concepts. And you've got a negative charge here, and let's say you've got another negative charge here. Now, you know, because of Coulomb's law, there's a force between these two, and there's also a force between these two. Now, I always say, please go and work out these forces separately, because if they ask you for the net force acting on this one here, so the net force acting on orange Coulomb over here, then you have to look at all the forces acting on orange Coulomb. And force diagrams cannot ever be left out. So if you calculate your forces first, and then you worry about the vectors. So you know now, this is going to be, let's just call it force. Okay, so I actually want to call it 1 and 2, that you can see how we like it to be written, but it's up to you. You can call it anything, but call the two forces something else. So this is the force between 1 and 2. So F1, 2 is equal to, and you work it out. Okay, Q1, Q2, and it doesn't really matter if you're using small or big Q's here. I know there's small ones there, but if it's just a Q, it's a Q, over R squared. Again, the distance between them squared. So you have the force between 1 and 2. Then you're going to do the same here, the force between 2 and 3. So here again, it's going to be equal to K, Q2, Q3 over r squared. And you go and calculate that force. Now the question said, what is the net force acting on charge number 2? So go and do a little force diagram. Look at charge 2. This force, there's a negative and a negative. Which direction will this force act on charge 2? And because they are repelling each other, this is now my charge 2 here, it's going to be pushing my charge 2 in that direction. So this is going to be F23 acting on charge 2. Now I look at this one. It's a negative charge and a positive charge. Are they going to repel or attract? They're going to attract, but I'm interested in orange Coulomb 2 over here. So it's going to attract orange Coulomb 2 upwards. So there we go. Those are the two forces. So this is F12. Those are the two forces acting on orange Coulomb 2. And once you have it like that, now you can do your vector calculation. Remember, if something is in equilibrium, so if it's standing still, then you're going to say that you can draw it as a head to tail. So you can say, there we go. We don't actually know if it's standing still, so ignore that bit. But they want the net force. If there's a net force acting on it, it is actually going to accelerate. Remember Newton's second law. So there's a F12 acting in that direction. Then there is a, remember, head to tail. What am I doing? That's not going that way. There's a F23 acting in this direction, but you draw them one after the other. It doesn't matter which one comes first. And then once you have them like that, we can go and say, I can now get my F net acting on that object. So how am I going to do this? And your math is pretty good. So we're just going to say from the start of this one to the end of that one. So F net acting on orange Coulomb 2 is going to be the square root of F23 squared plus F12 squared, and the green one there will give me F net. Now, please also remember, if they just said force, then you must add a direction because force is a vector. So to get this angle theta here, it's opposite over adjacent is tan. So you're going to say tan of theta is equal to F23 over F12, and you can do the maths and you get your angle. And then you can give a nice answer with a force with its size and its direction. Okay, so that's for forces. Now we need to also, again, remember, very important that there are two of them, because now we're going to go look at fields. And now it's going to be a little bit different. When we look at electric fields, it's quite a bit that we have to do here. But again, it's similar to gravitation. Because now if you look at the fields, yes, there are two different ones, but you're also going to draw them simple. Top, bottom, left, right, and go and draw one in between. For a field, the electrostatic field is defined as the direction in which a little positive charge would move. So if I'm a little positive and I'm sitting there, I will be moved in this direction. So if you look at the definition, yeah, it says define, it's actually the describe one. There we go. Is the direction in which a positive test charge would move. So if you ask for a electrostatic field at a specific point, always think, if you were a little positive sitting here, where would you go? This positive will push you away. This negative will pull you in. So actually, if you're at that point, you would probably have a resultant going that way. So look out for questions like this in a multiple choice. But they often ask you to draw these field lines. So positive, negative, make sure you can draw those. Those are really quite simple, but it can get more complicated. They can ask you to draw the combined field. So remember you have Siyabula, and these nice diagrams in the Siyabula book. Positive, positive, negative, negative. It shows you what the field will be like. positive away from the positive, negative towards, and then you can have the different combinations. So just make sure that you can draw all of these. Now, for fields again, similar to gravitational field, if I look at one charge, this charge creates a field around it. And we have already said that this field is, or that if there were two, there will be a force between them. But now, there is my field. If the field lines are like that, they could ask you to predict what the charge is. If it's coming towards it, it must be negative. So there's my field. So let's call this charge Q. Now again, this charge is creating a field around it. If I am a little charge there, or it doesn't have to be little, if I am a charge in the field of this charge, I am going to experience a force. And that again is the definition for electrostatic field. So electrostatic field is the force per unit charge. And if you think back to gravitation, it was the force per unit mass. So very similar. Now, if you're using this equation, remember this Q is the Q that is experiencing the force. But again, we have our whole equation that says the force between two objects, the force between two charged objects is equal to K Q Q over R squared. So if it's those two charges, so that's why I'm using the Q's like that. And you can see now if instead of the I can go and change this equation around again. So I can go and say that E is equal to F over Q. F is this, so it's K Q Q over R squared. But then I've already got a Q there or there as well. So the two Q's again, same as in gravitational field, will cancel out. And it gives me that new equation. And it's also on your information sheet, so you don't have to derive it. So it's just KQ over R squared. I'm just going to write it neatly. KQ over R squared. Now this one, when you're using this equation, is when you're talking about the charge that is creating the field. So it would be like the Earth was in gravitational field. So this charge is causing the gravitational field, and it has a field in this space around it. Now this one, so if I want to know what the field is at that point, that would be the distance that I'm using, because the field strength at that point is due to this charge. Then you're using your big Q. If you're using this equation, I need to use the charge that is experiencing the field. So please make sure again that you're using the correct E. Now, as in forces, they can also ask you for a net field. So please be careful. Read your question and highlight whether they're talking about field or whether they're talking about force. Because when they're talking about force, we need two charges. When they're talking about field, we need one charge. So if I have a charge Q1 here and I have a charge Q2 here, and they ask me for the net field, and it doesn't have to be in one dimension, but then they must give you the angles, or it must be 90-degree angles. So let's just say there's a little point here, point B, and I want to know what the net field is at that point. Very important, you need to think about the direction. If this is positive and this is negative, again, first go and calculate your fields. So you're going to calculate the field due to this charge by using E equals K Q1 over R squared. So this will be the field around Q1. It will only be one charge. Then you go and work out the field around Q2. Again, you're going to say K Q2 over R squared, and you work out this field. Do that because you're getting marks for the calculation. Do that before you do the vector problem. So now we can say, fine, I have a field here. This one is positive. So the field will always be away from a positive. So the direction in which another positive will move. So the E1 is going in this direction. Then if you look at this one, the field will be going towards it. So always towards a negative because a little positive will be attracted to a negative. So E2 is also going to be in that direction. So to get the net field, what we're actually going to do in this case is we're going to have to say that it's E1 plus E2. So go and work out this answer first because you'll probably get about 3 marks for it. Then go and work out this answer because you'll get another 1 or 2 marks for it, probably 2. And then doing the vector calculation will give you another 1 or 2 marks. So please know that vectors are important in this section. Now, what I want to do as a summary, it feels as if I've left out something here. I just wanted to check again that we have covered everything. So let's just fast do that because that is why we're doing this, to check that we've done everything in the SAGs. So we're going to do that quickly. We've done that, definitely. I'm going to look at that again. We've done all of that, solve problems using this. I haven't done actual calculations, but you've got the past papers. Q would be the charge responsible. I've just said that. And little q is the charge experiencing the electric field or the force. All right, so we did do everything. Now, this is what is important. Using your information sheet. Now, if you look at the information sheet, I said the first column gives you your laws. Newton's law of gravitation. A force between two masses will be directly proportional to the product of the masses and inversely proportional to the distance between them squared. See, now you don't have to learn it. Coulomb's law, the force between two charges, directly proportional to the product of the two charges, inversely proportional to the distance between them squared. Again, now you don't have to learn it. So the first column will give you the laws. The second column gives you the definitions. Gravitational field is the force per unit mass. Force per unit mass. Electric field is the force per unit charge. But just remember that it has a direction as well. But the direction doesn't have to come in the definition. And this I can actually put in brackets because you don't have to say that. It's just the force per unit charge. If you don't say positive charge, we also don't mark it wrong. So it's the force per unit charge. Now here is the describing thing. So we know that mass M will have a field around it. So it's a region in space, and this tells me where that region ends. So the gravitational field at that point there, so that's the distance between the mass and a certain point. It's the region in space where something, a mass, another mass, will experience a force. So these ones are not as clear as these ones, but it can still help you because a square means it's a region, it's an area, but yeah, you can just make sense out of it yourself. But it's if this mass is then creating a space around it where something else will experience a force. And for the field, again, it's the region where an electric charge will experience a force due to this charge. And then just remember that, the direction is the direction in which a positive charge would move. And that's fields. Now go practice.